Okay, great.
Okay.
So hi, everybody. I'm glad to be here today to moderate the workshop about how can AI help manage and predict weather-related perils in a changing climate. I'm Minetou Ndiaye, Sustainable Director in Axionable, and today I'm with Mrs. Giovanna Santi, Technical Head of Climate Risk in Allianz. Hi, Giovanna.
Hello.
And Dr. Alexis Hannart, Chief in Axionable. Hi, Alexis.
Hi, Minetou. Hello, Giovanna.
Hi.
Glad to be
Hi,
here today.
everybody. Yeah. So at first, let me introduce the two companies. Allianz is one of the greatest insurers around the world, with 100 million private corporate customers worldwide. And currently, they have 203 sustainable solutions provided. This is one of the greatest insurers. And what about Axionable? We are specialists in sustainable and responsible AI consulting. We are based in France and Canada, and we aim to solve real business problems, assist companies in creating sustainable value through responsible AI with impact and positive measurable impact too. So why are we here today? We are here to talk about the climate. We are here to talk about weather-related perils. And there is, I think, one important number. It's 210 billion. This is the global losses from natural disaster last year. And within this amount, insured losses are actually 82 billion. And as we can see, weather-related perils are diverse, costly, and they represent also a large share of natural disaster losses currently. And they are also ubiquitous, and I think this is one of the thing which make complex the problem. Natural disaster, as you can see in this map in 2020, was very ubiquitous, and they can affect all the geographic areas around the world. And right now, I think that we can also ask, actually, what about the climate in this context? About the climate, I think that we have two main numbers that have a real impact. Evolution of global temperature took 1 degree more since pre-industrial times. And the sea level rise are actually up to 25 centimeters, which is very important. And all these things are connected. We observe that overall, weather-related perils are trending upward. And as we can see it here in this map, we have a number of weather-related losses events worldwide, which increase more and more. And in this graph, we have also geophysical events, but the most important information is that we can observe a trending upward as a consequence of the climate change. And if we make a focus actually in Europe, in 2080, losses were largely dominated by drought in Europe. And overall losses from March to November in 2018 was about $3.9 billion, which is very important. And if we make maybe a focus in France, what we can observe is the fact that the trend is a little bit different. In France, the trend is less clear on narrower subsets such as drought, and it's also irregular. So as we can see, the period of drought in 2011, for example, or 2017 have been particularly tough. And this situation can allow us to explain why the problem is important in terms of damages. Why drought related to damages are we talking about today's use case? I think that the phenomenon is the clay soils shrink and swell in response to drought. And this is called subsidence, if I'm not wrong. And this subsidence causes substantial damages to buildings, which is a very important problem for insurers. And now I'm going to ask to Giovanna, actually, what kind of issue did Allianz want to address regarding these weather-related perils we talk about?
Thank you, Minetou. So more generally, France is very much exposed to weather-related perils because of its geographical position, because of its exposure to two main coastlines, one on the Atlantic, one on the Mediterranean, and its north-south as well as east-west spread makes it very vulnerable to a number of climate aspects. In 2015, Allianz and more generally the insurance market was very much proactive within the Paris conference, the Paris Climate Conference. And during this time, a joint report coming from IPCC and the Federation of Insurers, as well as the state reinsured, notified that by 2050, the amount of damages that would be related to subsidence will triple. And this, of course, has a major impact, not only on the insurers' accounts, but also on the way that the French state handles major events, major catastrophic events. I will come to it later. So just after 2015, we started encountering a 5-year stretch of increased or stable, increasing and stable in the high end of the range subsidence across France. And we haven't, which was somehow unexpected. So what was necessary for us to understand is to be able to predict as quickly as possible where our book of business was at risk, where it wasn't, and to be able to predict with the littlest surprise possible the outcome of those subsidence. More specifically, the French state has created in 1982 a national scheme to ensure that all its citizens are equally covered against natural catastrophe. What does that mean? It means that whenever you purchase an insurance for a property, you are automatically insured for natural catastrophes such as floods, such as subsidence, such as a number of weather-related perils. And not only weather-related, by the way. And this irrespective of your actual exposure to that peril. What it means in practice is that whenever there is a subsidence, so a drought, so an extreme swell and shrinking of the soil, there might be some damages. So every single municipality needs to go through a very standardized process and ask the state to be eligible to this natural catastrophe scheme. What that means for the insurer is that you will not know whether you have to pay for the damages until the commission that actually gives the eligibility declares the natural catastrophe to be so, declares subsidence to be so. And this can take as long as 15, 18 months. So saying that I am in the beginning of 2021, I still haven't seen all of 2019 subsidence coming through. And this is not acceptable for the accounts of a major insurer. We need to understand as soon as we can and as predictably as we can, as stably as we can, what is going to be the effect of the weather events onto our books. And we need to understand for the future how much of it is related to climate change. And that's how we got to Axionable.
Yeah, and this is a very interesting point regarding the prediction. And I think that, Alexis, maybe you have to tell some interesting stuff about this point, about the prediction of the decision.
Yes, absolutely. So thanks to both of you for the introduction and the problem. And here on this slide, I'm just going to restate what Giovanna has just said. What you're seeing in this chart is really the response curve associated to the decision-making process of the CatNat Commission that Giovanna was mentioning, which can be pretty long. So here it's really where the use case is. Our goal as data scientists and data specialists was to see how we can possibly predict the decision that is going to be made by the CatNat Commission in order to sort of soften the surprise and come up with an estimate beforehand of what the real payments are going to be after the decision has been made by the national scheme. So if you go to next slide, so I guess the reason why we thought that this use case was really amenable to a data AI approach is pretty trivial. It's because basically there's a lot of data on this problem. And to start with, we have the luxury here to have a pretty systematic and detailed historical view on all the decisions that were made by the Commission. Basically because it's official interministerial decrees, so they are published in the official journal of the French Republic. And this is something that is accessible and that we could access and use and document over an extensive period of time ever since this scheme is in place. So that's one aspect of the data, but that's not all. The other very abundant data that we have on this problem is really what describe the weather and conditions associated to this peril. In particular, the so-called hydrometeorological data is something which is really well documented over Europe, over France in particular. There's a data product which is called ERA5, which is a very also systematic way to provide really good spatial and temporal coverage for many variables related to the water cycle, being precipitation, but also the water on the ground, in the river, and also critically for this subsidence problem, the water inside the ground. And of course, this is information in both space and time at pretty high resolution. We're talking about a 25-kilometer resolution in space and hourly resolution in time. So that's a wealth of data too. That's not all. We also have an important data component for this specific problem, which is the description of the soil properties. Of course, not all soils respond in the same way to drought. Some soils are more prone to subsidence than others. And this is something which is very well documented at even greater resolution. Here we're talking about 50-meter resolution over the entire French territory by the French Geological Survey. Here this is static information, of course. It's not dynamic as opposed to the atmosphere. Fortunately, the soil is static. But so we have all this information at really precise levels. And of course, here we were working at the municipality level because the commissions take decisions for municipalities. But if you look at the geological information, it's actually at an even narrower level. Maybe Giovanna, you wanted to further comment on this?
Definitely. What Alexis is mentioning is that to an insurer point of view, what matters is actually exactly what kind of assets that he's being insured are going to be damaged. And that, of course, needs to be taken into account at a very precise level of resolution level. That means that even though we do have an understanding of the decision that is going to be made by the Commission on a municipality level, we need to go further down, and that's where these maps from the Geological Service come handy. On the other hand, what needs to be injected into the model is also something different, which is to say what sorts of assets are built onto this municipality. As Alexis just mentioned, of course, the soil reacts differently from the presence of water or not in itself. But on the other hand, construction themselves are also more or less flexible to the movements of the soil within this phenomena. So we need to understand how, first, the municipality will react. So will it be eligible to the national scheme? So are there going to be subsidence claims paid? And also at a much more granular level, how many of the assets that we do insure within these municipalities are going to show damages?
And in order to be more precise, I think that we have also some other data from Allianz during this process, right?
Definitely, because we do record, we have been recording for a number of years now, all the damages related to subsidence. And so we do have some claims records, 40 years old, that can allow for some, from some data AI, magic to happen in order to understand why it is that some of the buildings do react to subsidence and some others don't.
And Alexis, there is a lot of data, and maybe you can just talk a little bit about the AI-driven and the data-driven approach we use for this project.
Yes, absolutely. So if you switch to next slide, basically, once we have described this very rich and abundant data landscape, it comes pretty logically that you can somehow try to use a data science approach to basically piece together all this data and relate all the candidate explainable drivers to what we're interested in that case, which is on one side the decisions made by the CatNat scheme, which supposedly are going to be related to the weather and the geological conditions, but also to the actual physical damages that occurred on the portfolio of insured. And finally, by recombining the two, we can get what Giovanna was mentioning as being the end goal, which is really to have a view on what is going to be the final insurance compensation, given what has occurred in the atmosphere and on the ground, in the natural environment. And this is something on which we decided to use really an empirical approach that is completely driven by the data and our AI models.
And on my understanding, there is a lot of data sources in what you are talking about, weather condition, hydrological, the portfolio. So how can you manage all these sources of data, actually?
Yes, absolutely. So before describing the more data science part, this is more of the data engineering part, which was really substantial and critical in this project, because there is so many different data, and also, as was stated, so many different resolutions at stake, lots of work to basically ingest this data and then process it to reconcile all these level of information together in a way that can be properly handled then by the data scientist for training. So of course this requires some architectural work, and this is where, without diving into too much details, I can basically say that after scoping different solutions, we chose to use GCP, Google Cloud Platform, which here has been used for storing, processing the various data sources, setting up the right pipelines through the different data providers, and then also to train the machine learning models. And finally, we also did that because we wanted to be able to ensure the reusability of all our developments on other infrastructures, in particular, of course, the Allianz infrastructure for industrialization. So we use Docker containers for that. And I guess, yeah, I won't expand much more than that in the interest of time.
Yeah, of course, because I think that after the data sources, maybe you can explain us what was the modeling approach we used in Axionable.
Yes, absolutely. So this is where we dive into the more data scientist part of the work. Once all this nice architecture was set up, we could really dive into it and try to model our target variable, which in that case was really the final decision made at the municipality level by the commission. So it's really a binary classification problem. The decision is either yes or no. There's no intermediate decision. And then giving it a few thoughts, we decided to sort of split this problem into two less complex sub-problems. One which is, because of course to get approved, you need to make a claim as a municipality. So there's really one model that predicts whether a given municipality, given the conditions it had faced, will actually claim to the commission. And then the second model, which really models the decision made by the commission. So two binary models that are pieced together, and for which we've used pretty classical approaches. We've started with a very basic baseline, penalized logistic regression, and then we've progressively started to upgrade and get better performance by testing different approaches, and finally ended up with random forest. I think we also had gradient boosting on a tree approach, but eventually, so we get to the point where we thought we had sort of extracted all the juice from the data, and that gave us some results that we were reasonably happy with. I think you'll have a question about that, probably.
Of course, yeah.
But then I also wanted to mention another aspect of the data scientist work, which is really about reconciling these different resolutions. So as we mentioned, we have all these variables that come under different time and space resolution. And so there's an aspect of the problem which is about either downscaling some coarse data or upscaling some very fine data. Upscaling is relatively easy, downscaling is more tricky, but these are really aspects for which you can also use more or less complex AI approaches. In that case, the problem was not so critical, so we did something pretty basic. But there's really a lot of also hope on the use of AI for this sort of dealing with scale in general for this kind of environmental data.
Yeah, so we talk about data, we talk about sources, we talk about the model, but what were the result of all of this during this project?
Yeah, so I was saying that we were reasonably happy with the performance. Of course, I mean, as data scientists, you're never completely happy until you've reached 100% performance. But in that case, we reached a decent 83% in terms of classification performance measured by ROC AUC. So that's the curve that you see here on the right, which looks good. And translated in terms of accuracy on the actual decision made by the commission, this was very close to 80%. So at that level, we were already pretty convinced that this model was going to be able to produce some interesting benefits for the client, which I hope Giovanna will confirm. But one other way to view the performance here is also to look at it from the angle of, are we able to replicate over time decently well the variations that we're seeing across years on the rate of approval of the commission? And it's pretty strikingly obvious from this curve that you see on the right, where the prediction matches really well with the actual, which was also, well, was telling two things. One, that the model is good. Second, also that there is a really nice evidence that the national scheme is making decisions in the way that can be objectivized with the actual conditions in the environment. And there were questions. I mean, as always, when you have humans making decisions, you can always question whether the decisions are going to be made, you know, in a fair way, in a way that's constant in time. But here, that's kind of pretty positive evidence we see with respect to that question.
And if I may add just one single point, is that when we talked about it last time, when we decided just to stop at the point where at the rate of approval that we have reached at that point, we could anyways see that the difference that wasn't yet understood was somehow clear in a way, because patterns emerged as to something that was still missing from the model, but it was clearly missing. So that was also very much encouraging as to the quality and the explainability of the model, which is always something that is reassuring for the client, especially when you deal with technology that could be somehow opaque, which in this case isn't, because everything sounds and looks very logical and explainable, which to the client is a very fair point.
Yeah, this is very important. Yeah, go on, Alexis.
Yeah, and just to underline further what you just said, Giovanna, I think it's, to me, there's really room for further improvement. I think there is, I mean, we came up with a list of hypotheses as to, you know, additional source of information that could be used in order to actually explain the patterns we were seeing in the residuals. And I think one of it might be really related to something which is not there, which is descriptors of the buildings themselves.
Yeah.
Because of course, not every building is has the same vulnerability to the phenomena.
Of course.
Here we just have the environment. We don't have anything about the building really. And so, yeah, it might be some missing information that potentially we could add. We don't, by using, for instance, land use data or that kind of things.
And there was also another point that you didn't mention very elegantly, but also the political color of the municipalities that are being or not being made eligible or not. That's also something that comes out as a very striking pattern, that and the criterion itself was not integrated into the model, but it might as well be at some point in time.
Exactly. So this would be more of the human factor.
Exactly.
This is very, very interesting. And I just have one question for Alexis about the explanation of this level of performance, actually, because it's just impressive to have more than 80% of accuracy, actually. So how can you explain that?
Yes. So here I'm going to repeat a little bit what Giovanna was saying.
Yeah.
And we were feeling pretty well about this performance because we could explain at least part of it. I think there's really some pretty obvious signal in the data. When you see this curve here, it represents the soil water content at one of these nice little villages that France has, which we were showing on the previous picture, Huisseau-sur-Mauve. And so you can see clearly that a year in which a claim was made really stands out pretty clearly on the summer months. So when you look at the data and you see that kind of pattern, it kind of makes sense that, of course, the model is going to be good because it will pick that up. Then, of course, this is sort of an easy, very polarized situation. There are plenty of situations which are a lot more blur, for which it's more of the magic of AI in the sense of having, you know, related patterns that are not as easy to explain. But at least a great part of the performance is due to really reasonable and easy to explain influences of things that make physical sense.
And about this performance currently, Giovanna, can you tell us how does this performance translate in terms of economic value for Allianz, for your teams, and so on?
I guess that the major effect is going to be that the surprise effect will be mitigated in a major way. What's really important is that as major business do, we do close a balance sheet at the end of the year, and we had a very high level spread as to what subsidence claims would cost ultimately at the end of the year, especially because one, we didn't know the full of the year, and second, there was this whole eligibility and claiming process still to happen. So we had basically to look into the future, and we only had very basic understanding of what we would expect in terms of loads and how much it would impact our balance sheet. With this methodology, we expect to have a much better stability into our balance sheet, so that we don't have to adjust in the following years, and we are able to predict more accurately what we are to expect. So I guess that if the economic value in itself is the more stability to the balance sheet accounts that we can provide to our shareholders. Okay.
And what about the next step? Actually, because the result is fine, the performance is very good, but what are the next steps right now on this project, and almost regarding the long-term climate change?
So maybe I think one of the things that actually we had discussed at the very early stage of the project, before deciding to focus on the sort of near-term projection problem that we've described today, is really the longer-term view, where we would like also to address the question of what was the importance of climate change in explaining what has been actually seen over the past decades for Allianz as an insurer. Does that relate in a clear way to the change in the climate system, or are there other explanatory factors, such as change in the buildings, for instance, or change in the scheme itself, or whatever other candidate causal factors are here? So it's really the retrospective approach, which is to say, okay, maybe we can use this model to actually combine that with what has actually occurred in the atmosphere and on the ground, in order to sort of disentangle the different factors and make a clear case as to the influence of climate change is on this problem, looking back. And then, of course, there's the forward view, which is, once we understand what has occurred and the influence that has been measured on the past damages and compensation, you can ask yourself, well, what can we expect for the future? So here, it's sort of the game where you can also use the projections of the future climate that are issued by the large climate model simulations that are available, and process that through the model that we've shown today, and basically come up with simulations of what the actual damages will be for the future. So I guess it could be a natural way to pursue this effort, which is really to look at it on much longer time frames.
And definitely,
yeah,
I'm sorry.
Yeah, go on, Giovanna.
And on the insurer's point of view, there's definitely the double effect of how much it impacts its economics, and on the other hand, how much the insurer can keep on exercising its social responsibility, because of course an insurer is first and foremost socially responsible towards its customers, and especially within a national scheme that provides universal cover in terms of subsidence. It is major to understand beforehand what sort of impacts is going to happen, and to make sure that we allow for it into the major scheme of things.
Yeah, definitely.
Yes.
And maybe Alexis, you can also talk about the AI-based emulator. And
Oh yes.
yeah.
So in addition to what we've just said about projections and adaptation to future damages related to drought, which was the topic for today, of course you can sort of expand this approach to other type of perils. One of the peril that comes on the list that we had discussed also during this project after we handle drought is really flooding, which is also another big result-related peril in France and in Europe at large. Here it gets more technical because there's a lot of components of that problem that are really not that amenable to an AI approach in a straightforward way, because there's a lot of physics in there, and there's a lot of numerical models that are here to represent that physics. That's the case, for instance, for hydrological conditions, but also for flood itself. Once the river goes above its bank, what happens in terms of water depth in the inundation plain. So these are problems that are really difficult to address by using a purely empirical approach. And they are typically approached more in terms of using numerical simulations. But when you look at these problems in the context of climate change, and you have to basically run these models, these numerical models are pretty costly to run on very long period of time, it may become really very challenging in terms of computational cost. So this is where we see one possible benefit of AI as an emulator for these numerical models. An emulator is basically an AI model that has been trained to replicate the numerical model in a decent way, but at a much lower numerical computational cost. And so I think it's something that is basically, as a potential future for this project. We also have some R&D funding at Axionable to work on this. But that's clearly another use case that maybe we'll describe next year in terms of what we can do with AI in that weather peril management realm.
Oh, I'm sure that it will be a very interesting challenge for Axionable team.
Yes,
I'm just checking, well. and maybe Allianz too. I'm just checking the time, and let's see if we have some questions. All right, so I see any question, and maybe Alexis, we in order to conclude, you can talk about just in few words about the emulator in AI model in order to conclude.
Okay. Yes, certainly. So as I was saying, what we try to do with emulators is really to train an AI model in order to mimic what a physical model would do given the same boundary conditions. So to do that, it's the same paradigm as always. We use training data, which in that case are not originating from the real world. The training data is really the model boundary conditions and the model output. And we do our training on this and even end up with an algorithm that is able to replicate what the model does. So it can work in theory, I mean, conceptually for any kind of model, whether it's a hydrological model that would convert precipitation into runoff in a river, or on the next slide, whether it's a hydraulic model, which is one step further down in this modeling cascade that I was showing earlier, that would convert, in that case, the runoff of the river into a water level. So here, I think there's something wrong with the slide because it's the same image on both sides. But what should be shown on the, what should be shown as an output in that case is really what actually occurs in terms of inundation. And here, the reason we think emulators could be a good option is actually because there's already quite a lot of academic work that has been done to test this sort of approach. So here, what we're seeing on the screen is something, it's not something we have actually done at Axionable. It's from well, we've replicated it at Axionable. It's from a publication. On the right, this is the inundation simulated by a numerical model of this flood. Sorry, on the left. And on the right, it's the same, but using the emulator of this flood, which was emulated using a deep convolutional network. And we can see that the two are really very close. So the performance of these sort of emulations are often pretty good. But of course, it's really early work. So we are planning to do a lot more on this to test, extend, and make sure that this can be used in a reliable way in operations.
Wow, that can be a very, very interesting challenge for Actionable teams. So thank you, Giovanna. Thank you, Alexis, for this session. And thank you, everybody, for watching. Maybe see you next year.
Thank you, Minetou.
Thank you.
You're welcome. Bye.
Bye.
Bye.